Welcome to our webinar, Linear Regression and Interaction Effects. I am William O'Bannon of StatsWhisperer, bringing you the presentation. Visit us on the web at www.statswhisperer.com. Now, our agenda, pretty in sync with the title, right? So we're going to look at following the needed steps to conduct a linear regression, and after that, we are going to identify how to test for interaction effects beyond that linear regression analysis. Now here's a good question for you. Why would you or anybody want to use a linear regression analysis? So, point one is you could have a study with a continuous dependent variable, right, such as happiness. So if we're measuring happiness and it's on a scale of, say, 1 to 100, right, that's the dependent variable, and it's continuous, 1 to 100, 100 meaning more happiness, 1 meaning less happiness, right? That would be appropriate for a linear regression analysis. Also, if you have multiple predictors, also known as independent variables, right, that would be accommodated, by a linear regression analysis. So continuous dependent variable and multiple predictors of that continuous dependent variable. So, for example, what if you wanted to identify how 4 predictors or independent variables explain happiness, which is the example I just used, what a coincidence, right? So let's see what that would look like. So here we go. We have a nice figure here modeling the relationships we want to look at. So first, we have our dependent variable, which is happiness, and it is measured on a scale of 1 through 100. Right? So remember part A, that's what we're examining, so that's good for linear regression analysis. And then on the left side are our multiple predictors, our independent variables. The first one, many bills monthly, right? So say, does somebody have 10 bills a month, right? Then they might be coded as having many bills monthly, yes. If they have less than 10 bills, then no, they don't have many bills monthly. How does that relate to happiness, right? How does that predict your level of happiness? For education level, right? So we have here 3 levels of education: high school, the HS, C for college, and G for graduate school. How does having the highest level of education in one of those 3 categories impact your happiness? If we have humor, how does your level of humor, right, so it's also continuous. As humor goes up, does your happiness go up, or does it go down? Or is it not related, right? How does that relate to your happiness? And also aloofness, right? It's a predictor for aloofness. As aloofness goes up, does happiness go down? Does happiness go up? Does aloofness goes up? Or are they not related, right? So that is the question. I guess it's a bunch of questions within one question, right? The one question being, how do these 4 predictors explain happiness? And this figure can be modeled and examined through a linear regression analysis. Right? So if you write down your model, and it looks like this, right, with your multiple predictors and your continuous dependent variable, that's where you want to use linear regression analysis. That big question number 2, who would want to test for interaction effects, right? Well, it's when you believe, or one believes, that there is a third variable which moderates an independent and dependent variable relationship. So I put what in parentheses here because to most people that won't be meaningful. That's more of a statistical statement, right? There's a third variable that impacts the independent-dependent variable relationship. So we'll make sense of that right now. So for example, suppose we want to explain who the happiest people in our sample are, right? So we say that people that don't have many bills monthly will probably be happier than people that do, right? And also we might say that levels of humor might be associated with more happiness, right? Makes intuitive sense. But then we say, well, wait a minute. What if we think the happiest people are people with high levels of humor and no bills? We say, well, within that sample, if you could segment those people, you would find the happiest people there are, right? So when you look at our figure, you can see that you can't tell that by our, by this analysis, how it's structured. What we're looking at here are what they call direct effects, right? So when we say, how does many bills monthly relate to happiness? That's a direct effect. And then down here, the third, very independent variable, humor, how does that relate to happiness? That's a direct effect. But you can't see how the people with no bills and high humor in this model, you can't see their level of happiness, right? So that's why you need interaction effects. So this is the classic model of an interaction effect, right? So what we're saying is that in independent variable 3, right, there's a line going from that over to the dependent variable happiness. So we're saying there's a relationship between humor and happiness. And then coming up from the bottom, like in the old JAWS poster, right, is the moderating variable, many bills monthly. So when we say there's a third variable that moderates the relationship between the independent and dependent variable, this is what that refers to. So there's a relationship between the independent variable and dependent variable, humor and happiness. And coming up from the bottom, that arrow going up is saying that many bills monthly, yes, no, is going to moderate that relationship and explain it in a way that the direct effects could not explain. So let's make this a bit clearer also. So you might say, what are you talking about regarding this, this JAWS-looking structure, right? So if you look below, right, so you see below, this is what we're looking at. This is what that 3-box, 2-line consortium of figures is talking about. So we're saying that if you took humor, right, see on the left here, and you made it low humor and high humor, right, low and high humor, right? So first you're separating that independent variable out, and then next you said, well, within low humor, okay, you have people that have many bills monthly, yes, and people that don't have many bills monthly, no. And those two groups, right, within low humor are going to have 2 happiness scores, right? All right, follow me so far. And then we have high humor. Okay, so we're saying that the next category is high humor, and that within that group, there's 2 categories: those with many bills monthly, yes, and those without many bills monthly, no. And they're going to have 2 happiness scores too. So we end up with actually 4 happiness scores for these 4 groups. And our hypothesis was, is where the asterisk is right here, our hypothesis was The highest level of happiness are going to be for people that have high levels of humor and not many bills monthly. Right? So let's approach now the actual doing. So we've conceptualized a little bit, right? So now we want to actually do something. And since our first task was to do a linear regression, that's what we'll do first. Now the first step in a linear regression is examining test assumptions. Now, a lot of people, even a lot of experienced people, skip the looking at test assumptions. And most people actually skip it just because they might not be aware of it. However, skipping the test assumptions can skew the results and make them look significant when they're not, or not significant when they really are. So the mark of a good, efficient, professional, sophisticated analysis is, of course, to look at these test assumptions. So we have 4 that we must consider. Right? So a normal distribution, multicollinearity, homoscedasticity, and linearity. Right? So all 4 of these need to be checked. And if you're going to, I'll reiterate this later, but if you read a research article or a research report, any sort of research, and they use linear regression, they should always report that these test assumptions were checked for and met. And if it only takes us, even if it's just a sentence could say, we examine normal distributions, multicollinearity, homoscedasticity, and linearity, and we found that the test assumptions were met. So it could just, optimally it could be a little more descriptive, but it could be one sentence that states it. So if there's no mention of it, at times I worry that it hasn't been done, even though it may have been. So it's just, but if they state it has been done, then at least you can assume it has been done. So testing for the normal distribution. If anyone does any of these, they test for this. Right? So there's 3 steps to testing for normal distribution. First, you want to test for normality. You want to see if the distribution is normal. And if it is, you might be okay stopping right there. If this is regarding, of course, continuous variables, right? So, because if it's a categorical variable, you don't need this, right? So it's continuous variables, right? So you want to make sure you have the bell curve, right? The bell curve shape and normal distribution are approximately normal for the continuous variables. So if it's not normal, the distribution, you may want to check for outliers, which are extreme scores. So happiness is 1 to 100, and the average score is 50, and then you have one person that's 100, they're very happy. It's a very high score, and that could skew all the results. But their regression could be significant just based on that one guy score, and that's one of the reasons you need to make these checks, right? Because that's not a true finding. A true finding is, it's a finding within the population, right? Right? But if it's just one person causing the result, that's not a true finding. That's just an aberration. So looking at outliers to fix the normal distribution, and they have data transformations that they do also. We'll go through those. Those are like log odds. Those modify the variable, so there's a more even distribution. But we'll go through that. Okay. Now the testing for normality. So this is a normal distribution, right? So we see, right, the bell curve shape. Now you'll notice in the center we have a 0, right? And so that's the middle of the distribution, right? And then the 1 to the left is -1, and the 1 to the right, +1. Those are the standard deviations away from the mean. So you can see as you go up, 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 follow those lines, you see the 68%. So that means for a continuous variable in a normal distribution, 68% of cases, which is roughly 2/3, are within one standard deviation of the mean. So if you were going to take IQ scores, right, so if the average IQ score was 110, right, 2/3 of the people would be one standard deviation above and below that average score of 110, right? They would be clustered around the mean, right? And as you go out, right, so that would be the average IQ score here. And as you go out, right, there's the lower IQ scores, and there's the upper IQ scores. It's almost, intuitive. If you go out and gather 100 people, you're going to figure most of them are going to have an average IQ. And some of them might have, kind of lower IQ, and then some of them will have a kind of higher IQ. It's just, intuitive for what you expect in the population. Right? So here's our normal distribution. If our distribution looks like this, then our assumption of a normal distribution is met. Now what are the threats to a normal distribution? Poor skewness and kurtosis, meaning poor meaning not good. So what are those? So skewness, right? So you get that peak. If that peak is favoring one side or the other, right? It's not in the middle, it's to the right or to the left, they call that a skew, right? So the negative is skewed to the right and the positive is skewed to the left, right? So, for example, if you were taking IQ scores and there was just a Mensa meeting that let out, right, it might look like the distribution on the left here, where the scores are skewed to the right, right, because the mean score, the average score, is much higher than where the normal, in the normal population, right? It would have been in the middle, but for some reason it's higher, where the scores are higher, because you have a bunch of Mensa people. Okay. And then also kurtosis. Where the skew refers to the peak, the kurtosis refers to the distribution, right? So that's the cases going from the peak out into the tails, right? So we see A here, that's good kurtosis, right? See, like, it goes up, it looks just like the other peak, right? We have the peak in the center and like full tails. So you have the average scores, a little below average, a little above average. So C, there's no one in the tails for C, right? So what that's saying is there's a bunch of average scores, but the little more low scores and the little more high scores are absent, right? There's no one in the tails there for C. Right? And then this score right here, that's saying that there's no peak, right? There's no peak right there. The scores are kind of just distributed out to the left and right, right? So they're all kind of just flat, right? So checking the skewness and kurtosis is how we check the normal distribution. One of the best ways, right, to check for poor or good skewness and kurtosis is to see if the standard is to look at the standard error of the skewness and kurtosis. And so we're going to look at this, but it is said that if the skewness or kurtosis is not 2 times more than the standard error of the skewness or kurtosis, and you can use 3 if you want to be a little more liberal, right, then it's approximately normal. And it's a good rule, and it's applied to various samples, right, like meaning that you could use it for large samples, and you could use it for smaller samples. A lot of the tests for poor skewness and kurtosis refers to large samples. So this is a good one you can use for large and small samples. Right, so let's look, for example, at the variable age. And we'll look to see if the age, which is a continuous variable, right? You start with 0, you go to 90, 100, right? And as you go up, there's more age. If you go down, there's lower age, right? So it's a nice continuous variable. And we can look to see if age is evenly distributed. Okay, so let's actually go into SPSS. All right, so here we have our SPSS database. And we go to Analyze and Descriptive, and this is all on the slide, Descriptive Statistics and Frequencies. And under Statistics, well, we want to click Skewness and Kurtosis and Continue. We take age, and we put it over here, and click OK. So there we go. You see right there. You have skewness, right? Age. There's a skewness, 0.981 standard error, the kurtosis, and the standard error. So these are in the slide listed. So, right. So here's our path that we followed in SPSS. And there's our skewness and kurtosis that we computed. So you see, right, so all you do 0.98 by the standard error, which is rounded down to 0.34, which comes out to 2.88. So if you're saying it can't be twice, the skewness can't be twice the standard error, then this is not normal. The same with the kurtosis. Right? So you got your kurtosis, which you rounded to 4.54 over 0.66, and it's 6.88, which is very non-normal, right? So what do we say? We do if we have a non-normal distribution. We say outliers, right? We take a look, and we want to see if there are any outliers that are making the distribution non-normal. Right? Like we said, it's not only that it makes the distribution non-normal, the outliers can make significant findings look not significant, and the other way around, right? This is an important thing. So if you see a linear regression analysis reported and no examination for outliers, you know the findings might be questionable. Right? So here we go for the outliers. We use the explore function where we go analyze, descriptive statistics, explore. We'll put in age, and under plots, we'll check stem and leaf, and then we'll get our outliers. So let's actually do that. So here we go. So we go to analyze, descriptive statistics, and explore. Let me take our age, put it there. Right, and under plots, we click stem and leaf. It's already clicked. Right, and continue, and then OK. And then it takes a little while for SPSS to produce the stem and leaf plot. Right? Well, let's just yeah, for people that have used SPSS, this is nothing new. There we go. So here's stem and leaf. There's processing. Well, let's just go actually to it's on the slide. Here we go. So here we go. We have our path, and there we go. There's our stem and leaf plot. So what the stem and leaf presents is that 1 and 2, right? 1 and 2 are outliers. That's case 1 and 2. Case 1 and 2 are outliers, right? So that's what the plot looks like. If we were to kind of dissect it a little, sort of looks like this is what that is. So the 1, which is way above, so you see the scores on the left here, that's the high outlier. So the median value, you can see, is between 40 and 45, okay? And then you have one outlier that's a high score that's way up there in between 50 and 55, and another outlier that's a low score that's between 35 and 40. And so stem and leaf tells us what the outliers are. Right? So if we go back to SPSS, yes, there's stem and leaf. There you go. So it looks just like we had it. Okay? So if we go back, we can remove the outliers. So I've actually created, I took the outliers out right there. So there's our low outlier, the one of 37, right? That's the one below. And then our high outlier between 50 and 55, 52. So we have age and we have age, the same variable, it's just with the two outliers removed, okay? So then, if we go back, we want to test frequencies, or the right frequencies. We take age out, and we put in the age with the two outliers removed. And again, we still have checked skewness and kurtosis. Then we click OK. And look at that, it came up fast. How about that? So we have our skewness, standard error, the skewness and kurtosis, and standard error, and here are the numbers. And let's see what happens when we divide them. So our new skewness is 2.65, and the new standard error is 0.343. And then when we divide that, it comes out to 0.79. Right? So remember before it was 2.88, it was pretty close to 3, it was pretty high. Now it's below 1, so that's much better. And then the kurtosis, which was over 6.0, right? It's very non-normal, is now 1.32 divided by 0.67, which is actually a little less than 2.0. So by removing those two outliers, the distribution becomes normal, right? And now we meet that assumption. So it's quite a bit of work, but you know, it's doable and it's the right thing to do. So log odds. What are log odds exactly? Well, it'll take like that variable, like the untransformed age with the outliers in it, and instead of removing those outliers, it'll multiply each score by the same number, and that'll help the scores spread out, and the distribution might be more normal because of this multiplication and this transformation of the variable. Now, I'm not so high on the log odds because when it does that, it changes the actual characteristics of the variable. So what happens is if the mean score is really 38, if you do a log odds and it transforms the variable, the mean might be reported as 45, which is, you know, not the real mean. It's off. The mean is actually off because the variable has been altered. So I'm not so big on the log odds. I'd like to take different steps before I get that crazy, right? So what to do? What would you do? So here's what I usually do. To account for a non-normal distribution, I would do the regression model with and without the modified variable. So I would do the regression model per se with age with the outliers and with age without the outliers, so with and without the outliers, right? So to the second bullet, if the results are similar, right, as in significance levels, So if age was significantly related to happiness with the variable with the outliers removed, and then age was related to happiness with the outliers included, I would just keep in the original variable, age with the outliers included, and then you might just report it in the message. Age was not normal, but the results statistically significant results were the same with and without the variable, which is usually the case, being transformed. So that's usually the case, right? Because it's said that the regression models are robust, which means they can handle these non-normal distributions. And so that's what's said, right? But if the results differ, right, bullet point 3 here, if the results differ, consider doing the log odds transformation. And the log odds transformation is simple. I'll show you how to do it really fast. Just knowing about it is really half the battle, because in my experience, it's not the fact that people can't figure out how to do things, it's they don't realize the presence of that option. Right? So if I say there's a log odds, you can always look into it and do it. Most people's problem is they don't know that such things as the log odds exists. But really fast, this is how a log odds would go. So you got happiness, right? And you go to transform and compute variable. And then over here in the function group, as you click all, you'll see there's an LG. There you go. So I say LG10. You put it up there. Then you just take age, right? And you just put it in that space right there. And then you just rename the variable. So maybe age log odds. And then you click OK. Right? And then if you look under here, way over here you go, age log odds. So there's a version of the variable age that has been transformed for, with the log odds function, and you could test that for normality. Although I could tell you now, it doesn't usually do as good in fixing the normality as removing the outliers. Okay. So there we go. Now, multi-collinearity, right? So not only are they hard to do for some people, but as you can guess, they're hard to say for a lot of people too. Right? So multi-collinearity generally refers to the independent variables being correlated at a level. Again, usually, the continuous variables being correlated at the level where it seems that each is explaining the same variance in the dependent variable. Meaning, if the dependent variable is happiness, say we had two measures of humor. One was like telling jokes and the other was laughing at jokes. And the two measures were really highly correlated because people that tell jokes also tend probably to be the people that laugh at jokes, right? So they're each kind of reflecting the same thing, humor, but to two separate measurements. So if one explains some variance in happiness, right? So suppose one explains 10% of the reason that the happiness scores go up and down. Well, then the other might, if they're correlated very highly, the other might explain the same 10% because it's generally the same construct. And you'll find this with other things such as, age and level of education in, in samples with people up to their 20s and 30s, because as age goes up, their level of education also goes up. And sometimes it almost is like the level of education reflects the level of age. So it's explaining the same, explaining the same thing within the sample. Right? So, very simple to examine, and we'll look at it when we get to our regression model. But when we run our regression model, right, we just make sure, at the last line here, we click tolerance, and we click collinearity stats, and it'll give us the tolerance and VIF. And what will that do, right? So if the tolerance is not below 0.10 and the VIF is not above 10.0, then we assume that we assume that multicollinearity is not an issue. Okay? So these are kind of simple indicators, so you know right away if something's going on you need to address. Now, linearity. What is linearity, right? Well, you have a linear regression. Right? It sounds similar. Right? So you have a continuous independent variable, dependent variable, and they should have a linear relationship with one another if you're using linear regression to examine that relationship. So what's that mean? That means this. Right? So the first one here, we have linearity. So it's a positive relationship. So you can see the dots as you have one increase on the x-axis, you have a 1 increase on the y-axis, right? And then as you have 2 on the x-axis, 2 on the y-axis, and then it just keeps following up from there to where the dots meet at the 5 and 5 juncture. Now the second figure is linearity. It's just negative. So if you have a 1 on the x-axis, you have a 5 on the y-axis, and then it goes down. So if you have a 2 on the x-axis, a 4 on the y-axis, all the way down to having a 5 on the y-axis, right? So here's our issue. For example, the third one, when there's collinearity, a curvilinear relationship. So that means that, right, in the beginning, 1 and 1 meet, 2 and 2 meet, 3 and 3 meet, but after you get past 3 and 3, right, the relationship starts going down. Right? So as y gets higher, x gets lower. As x gets higher, y gets lower, right? So that's a curvilinear relationship, and that's no good for linear regression, because linear regression is assuming that there's a linear relationship. And homoscedasticity, that refers to, right, a homogeneity of variance, meaning the data points are spread out evenly, right? So if we're trying to explain scores from 0 to 100, and all the scores are kind of bunched up at 100, well, it's hard to explain scores from 0 to 100 because the scores aren't kind of evenly distributed to explain. Okay, so that's what this is more or less referring to, right? Now, although linearity and homoscedasticity are interesting to look at, testing for them actually can be quite straightforward. So when we go into SPSS, right, we'll go to our Analyze Regression Linear. We'll put in our models where we'll put in the dependent variable and independent variables. So under plots, we just go to the Y and X boxes and we enter Z-resid and Z-pred, okay, and then click Continue and OK. And that distribution, or the box that comes out, the scatter plot, we can see the linearity and homoscedasticity from that. So let's just really fast take a look at that in SPSS. So we have our Analyze and our Regression and Linear. All right. So you put our happiness in the dependent variables box. Then we want to put our predictors, so mini bills monthly, right? And then college and graduate school education, humor, and aloofness, right? So we put all those in there, then we go to those plots, right? And we put z-res and the z-pred, right? Oh, let's see, right? And then z-res right in there. And then we, okay. And then that runs like that, and this is what it gives us. Right? So there you go. So there's good homoscedasticity and linearity if there's kind of a random dispersion of scores around the zero, right? See, it's all just kind of scattered on out, and that's a good thing. Now, if it's not scattered, and there's this funnel shape like this, that's supposed to be not good homoscedasticity, and that's referred to as heteroscedasticity. Excuse me, right? The funnel shape, right? So if you get the funnel shape, that's not good. But if you have the dispersion, that is good. And that's usually what comes up, for me anyway. And then the linearity, right? So if it's randomly dispersed, it's good linearity. But if we have this kind of this shape with curvilinear, right? That's not good linearity, right? And we want to watch for that. All right, so the test assumptions, right? So this is often the most work done in the linear regression analysis. And as you can see, it's often the most work, especially if there are issues. Just testing for it is a job. But if there are issues that need to be addressed, that's a job in the job, right? It's often the most skipped, right? The most skipped step. And like I said, if it's not reported in an article, that could be cause for concern. So now you'll have that level of sophistication to know.